Gang, the purpose of this video is more on hypothesis testing, and I'm a firm believer that regardless what you're doing, uh, whether you're learning to play golf or shoot a basketball or make free throws or sew or cook or clean or whatever it is, uh, if you want to learn how to do it, you got to do it, right? If I want to learn how to, for example, I'm going to go scuba diving here in the next few weeks. The best way to learn to scuba dive is to go scuba diving. Well, somebody just Facebooked me, so I'm getting distracted. But what I want to do here, one of the most confusing parts of hypothesis testing is looking at the two different methods. And you know the method I looked at in the last video was called the p-value approach. And what the p-value approach does primarily is it compares the p-value, which we get from the test statistic, to this alpha level called a level of significance. And from this, we make one of the following decisions. We either reject or fail to reject a null hypothesis. Now, what we did previously, and I'm just going to bring up a problem that I did in the previous video, if I can remember it. I think I said something to the effect that we were going to test that the mean final exam score for students taking Math 1500 was higher for online students than it was for traditional students. And I decided, for obvious reasons, I think, because it's the industry standard, that I would test at 0.05. My sample data, I think I had 24 students. I think their average on the final exam was 83, if I remember correctly. And the standard deviation was 19. Now, this would be really, really easy to carry out with our calculator, which we did. We could go into stat, go over to t-test. And we're doing a t-test because, as I explained in the previous video, if we're testing a claim about a population mean and the population standard deviation isn't known, then we use a t-test. All right, so, and it turns out I've got the information in my calculator. That's kind of cool. I didn't realize it would be there. And I calculate. And primarily when I hit calculate, what I'm looking for is the p-value. And the p-value in this case is right there at p. It's 0.2235. Now, a lot of times students will say, well, Dr. Darbo, where's the alpha? The alpha isn't there because alpha changes according to the kind of the conditions of the test. Sometimes it's just the researcher's preference, but typically researchers just go with the 0.05, which again is the industry standard, but there could be reasons to fluctuate that. Probably for things we won't actually discuss in this class, but there could be reasons. But we're going to consider 0.05. So what I would do, I have tunnel vision on my p-value, which was 0.2235. That's clearly bigger than my alpha. So my decision here would be fail to reject. So I would fail to reject the null. This is called the p-value approach. This calculates the test statistic, either using your calculator or doing it by hand like I taught you in the previous video, or at least I hope I taught you, and it calculates the p-value based on the test statistic. So you got to have your test statistic first, then it calculates the p-value based on the test statistic and the alternative hypothesis that you're using. And again, it compares it to the alpha. If our p-value is greater than alpha, then we fail to reject. If our p-value is less than alpha, then we reject. So in this case, we would fail to reject. Now, how does that differ for the critical value approach? Well, first of all, the critical value approach doesn't use a p-value. So I want to illustrate here the critical value approach. Okay, now the critical value, just like the p-value calculation, depends on the alternative hypothesis. So if in our alternative hypothesis we have a greater than, then we are going to try to find the value. And I'm going to call this my T critical, that has alpha area to the right of it. We're going to call this our failed to reject H sub O region. We're going to call this our reject H sub O region. If our H sub A is less than, then we're going to go to our left tail, and we're going to find the T statistic that has alpha area to the left of it. This is going to be called our reject region, and this is going to be called our failed to reject region. The third option, which would be really handy if you could see it, is the not equal to. In the not equal to region, since we've got two tails of rejection, we're going to try to find the T critical. Now, let me point out one thing. Back here in the less than, this is going to be a negative T. Okay, so we're going to find the negative T and the positive T critical that has 1/2 of our alpha area, 1/2 of our alpha area up here. This will be a reject region. This will be a reject region because at the not equal to, it's not a directional test. We don't care if our result is above or below. What we care about is it far enough away from the claim to just consider that it's too far away. And of course, this is the fail to reject area. Now, let's go back to our original problem. Our original problem, what did we want to do? We wanted to see if there's enough sufficient evidence to conclude that the mean final exam score for students taking the Math 1500 course online is higher than 80. So guys, my alternative hypothesis has a greater than. So I'm going to come to the example for greater than, which just happened to be this first one. And I need to find the T critical. Now let's go back again. What was my alpha? My alpha was 0.05. So I need to find the T critical that has 0.05 area to the right. All right, so let's get this in a big drawing where we can see what's going on here. So the first thing we do is define our regions. We want our reject H sub O region and we want our fail to reject H sub O region, but we've got certain criteria that has to be met. First of all, we know that this curve right here is the t distribution. Degrees of freedom equals 23. Because guys, we had back here, we had a sample size of 24, right? We had a sample size of 24. So the degree, the sampling distribution that we deal with, the t distribution, and it's a t because we have a claim about a mean. The samples, the population standard deviation is not known. So we take one away from that. So we're working with a distribution degrees of freedom 23. Second thing we know is that our alternative hypothesis is greater than. So our rejection region, there's going to be some value here that's going to separate the reject region. And the fail to reject region. How much is up here? Alpha. So our alpha is 0.05. So guys, at the end of the day, what we're trying to find is we're trying to find the t critical value that has 95% of the distribution below it. Well, guys, that's easy to do. Distribution, inverse t. Let me get rid of all this other stuff. .95 below it, degrees of freedom 23, 1.714. That's it. That is my t critical value. Now, the way that the critical value works out compared to the p-value approach. The p-value approach compares the p-value with the alpha. The critical value approach finds the area our test statistic falls in. Well, guys, let's remember our test statistic was what? 83 minus 80 over 19 divided by the square root of 24. You may remember that. I don't. But I don't care because I can get it real quickly. It's 0.77. 0.77. Now this 1.714 is the line in the sand. This 1.714, and guys remember, in the center of the distribution is mean 0. These numbers over here are negative. These numbers over here are positive. 0.77 falls about right there. This is 1.71. So it would take a test statistic above 1.714 to get us to fall in this area up here, which is the reject region. So you make your decision on reject or fail to reject based on where this line in the sand separates the fail to reject and the reject region. And our 0.77 fell to the left of the 1.714. Therefore, our decision would be fail to reject. Now, you're not going to get this the first time through. If you just want to watch one example and say, yeah, whatever, you're probably not going to get it. You're not going to get it really well, not the way I want you to get it anyway. So, again, I think the best way to learn this kind of stuff is just work examples. And what I do in each example is I change a little bit, mix it up a little bit, and work through with you how we work these particular types of problems. All right, so the following data are collected on What? The following data was collected. Okay, obviously there's a grammatical error there. But anyway, it looks like we got 5 randomly selected vehicles. And these are miles per gallon for 5 vehicles. And it will ultimately use the data to test the claim that the average miles per gallon for this vehicle. Now, this is only 5 of them. Let's just say that these are Ford Taurus, whatever. Well, we know there's more than 5 Taurus, but we've chosen 5 randomly selected, whatever this was, in the miles per gallon for those 5. So we want to use that to make kind of a statement about all Taurus. So we want to test the claim that the average miles per gallon for this vehicle is different than 24. Well, it doesn't matter what approach we use. The first thing we have to do is set up the null and alternative hypothesis. Remember, guys, come to the alternative hypothesis first. So mu not equal to 24 would be the alternative. When the alternative is not equal to, the null hypothesis is just going to be equal to. Now, the p-value approach, in my opinion, is easiest and most effectively carried out by using the p-value approach. I'm sorry, by using your calculator. So let me illustrate that. Guys, this is a little different because I've got my numbers. So I'm going to go into edit. I'm going to clear out L1. Remember doing this many moons ago. And now I'm going to carefully type those 5 numbers in L1. All right, go back up. Just to be safe, when your grade's at stake, make sure that number represents how many you're supposed to have, which is 5. I know that my standard deviation for the population is not known because it's not given in the problem. So I do a t-test. Guys, this time I got my data. So I'm going to hit enter. I want to test claim of 24 using the data in L1. I want my frequency to be 1, but I want not equal to. Now guys, when I hit calculate for the p-value approach, what do I have tunnel vision on? My p-value. Is it bigger than 0.05? Is it less than 0.05? And guys, my p-value is right at 0.80. So my p-value .799 is greater than my alpha up here. So what's my decision? Fail to reject the null hypothesis. So is there sufficient evidence to claim that the average miles per gallon is different than 24? No, there is not. There's sufficient evidence that the mean is 24. There's not sufficient evidence that to conclude to support that the mean is different than 24. The critical value approach, guys, it's more involved. You can use your calculator, but you got to do more work. What we got here? We got a t-distribution. Degrees of freedom equal to 4. We had 5 numbers, 5 miles per gallon, 5 minus 1 is 4. Because we're doing a two-tailed test, we create 2 regions of rejection. The amount we put in each tail is half of my alpha. my total rejection region always has to add up to my alpha. My alpha is 0.05, so this rejection region plus this rejection region has to add up to my 0.05. Now, because of symmetry, I just need to find one of these. I know that this one's going to be the negative, and I know this one's going to be the positive. They're going to be the same number, just a difference in sign. So guys, can we do that? Well, absolutely we can do that. It's easy. I'm going to find the left one. I don't know why. I just am. Okay. Inverse, so I need 0.025. Degrees of freedom, 4. The left bound is negative 2.776. What's the right one have to be? 2.776. Now, someone says, well, I don't understand why that one has to be, you know that one's positive. Well, guys, if we just do this again, and instead of having let's have 0.975. Now, why 0.975? Well, from here, we've got, what? 95 plus 2.5, 97.5. So, guys, you'll see that you get the same thing. All right? Now, where is our test statistic? Our test statistic, which we can actually get from our calculator. If we're tricky enough, we don't have to do all that by hand. We can go t-test. We've got the data, 24, L1. Got that set correctly? Come calculate. This value right here is our test statistic, negative 0.272. It's the t-value. That's our test statistic. This is the p-value. Test statistic, p-value. So test statistic is negative 0.272. And where does that fall? It falls right there. It falls in our fail to reject region, just like we found back here. Two approaches doing the same thing. Now, which one's easier? I think your p-value approach is easier. But guys, there are times, there are situations out there where you have to come up with your critical value to make certain decisions. Okay, so that's the reason that we teach both. Now, your critical value really comes in a lot more when you delve into confidence intervals, but nevertheless, something that we teach in statistics. All right, guys, I just had okay, cool. All right, now the next thing I want to do is use the data to test the claim that the average miles per gallon for this data is for this vehicle is less than 24. Well, guys, this changes our alternative hypothesis. So mu is less than 24 in the way that Hawks is going to want you to put in the null hypothesis is mu is greater than or equal to 24. Okay? P-value approach. How are we going to do this? Calculator. If so, there's going to be problems coming up, and you're going to have one in your final exam where you can't use your calculator. When I say you can't use your calculator, you can't use t-test directly. You've got to use that t-CDF that I talked about in the previous video. If you haven't watched the previous video, guys, you need to. You've got to put all this together. So, guys, in this, all we would do, we got the same information exactly. All we need to do is just change that to less than. Choose the same inequality right here that you have right there. This one's pointing to the left. Choose the one that points to the left. You'll see that the test statistic stayed the same, but your p-value changed. Your p-value is now 0.399, but doesn't change the results. it's still bigger than our 0.05. So regardless whether you test that it's different or if you test that it's less than in this problem, it won't be always the same thing in each problem. But in this problem, you're going to fail to reject. So there is not sufficient evidence to conclude that the miles per gallon is less than 24. There's sufficient evidence to conclude that the miles per gallon is 24 or higher. Okay. Now, the critical value approach. What do we do first? Guys, we tap into this right here. What's the sign? What's that tell you? You're dealing with the same distribution, degrees of freedom 4, but because you have less than, you're putting all of your rejection region in the left tail. Your fail to reject is everything to the right of it. Hence, greater than or equal to. Everything greater than or equal to, okay? Anything less than 24, we're going to reject, okay? All right, how are we going to find that? Remember, guys, now we put all of our alpha in that area. So we're going to use inverse t, 0.054. Before we used 0.025, but that's what you do when you conduct a two-tailed test. You split the rejection region. You split your alpha into two rejection regions. So gang, inverse t, 0.05, comma 4. You have negative 2.132. Well, our test statistic doesn't change because your test statistic is this, and now that changes. And we saw earlier that it was negative 0.272. So this value, again, remember zero's in the middle. So it's still going to be about right there, which says we still fail to reject. Doesn't change any. Won't always be the case. Sometimes you get into one-tailed test versus two-tailed test and you get different situations. All right, gang, going to throw something a little different at you here. I think that's the best way to learn. Sometimes the best way to learn to swim is just get thrown in the river. Well, probably not. All right, number 2, results from a nationally based research firm indicate that 5.8% of job applicants fail their initial drug test. Okay, so apparently we're doing some drug screening tests. I don't remember this problem. In a recent sample of 1,520 job applicants in the Southern Ohio, I do remember this too, Southern Ohio region, 109 failed their initial test for drugs. At the 0.05 level of significance, use the sample data to test that the percentage of job applicants in Southern Ohio who failed their initial drug test is higher than the national. Use the approach for the p-value. Okay, I want to do the p-value approach first because, guys, the p-value approach is the easiest because you've got a calculator key that does that for you. But nevertheless, we need to set this up. And just as before, go to your alternative hypothesis first. And we want is higher than nationally, so we want to see if P, because it's a percentage, is higher than the 0.058 that's been reported nationally. So guys, opposite of this, again, I prefer just to put the equal there, but your textbook prefers less than or equal when you have a one-tailed test, less than or greater than. Doesn't work that way with not equal to. And the alpha level here is 0.05. Now the next thing we need to test is our sample. And guys, for means, for testing the mean equal to, you will have n, x bar, and your standard deviation. But you're not doing one of these. You're not testing mu equal. You're testing that the percentage, 5.8%. So your sample in this situation is p hat as an x over n. P hat is your sample proportion. We talked about this before. X is the count out of your sample that has the characteristic you're measuring. N is your total sample size. So for this problem, our total sample size would be all of the people in Southern Ohio who took an initial drug screening test. And then X would be the count out of the 1,520, namely 109, who failed. So let's put that in our calculator and see what we get. So we go 109 divided by 1,520. So this is 0.0717, which is approximately 7.2%. Now, a person that knows squat nothing about statistics would say, well, we don't need to do anything else. 7.2 is bigger than 5.8, so done deal. Well, it's not a done deal. In fact, for people who have completed a statistics course and say crap like that, it shows me they don't know what they're talking about. This 7.2 is for this 1,520 people. We're trying to generalize to all applicants in Southern Ohio who are failing their drug test. That's only 1,520. We're probably talking about hundreds of thousands. We're trying to generalize from this 1,520 to all Southern Ohio applicants, okay? This 7.2 will vary from sample to sample. Is that difference from 5.8 to 7.2 just a result of sampling variation? Because we know these samples will vary? Or is it the result of something else? Is it the result that we have a problem in Southern Ohio with people coming to start a new job who are been using drugs? Well, you know what? You just let the process play out. Now, guys, you have a different test here. This is not a t-test. This is a one prop z-test. So, guys, one prop z-test is a little bit easier because there's not as much stuff to put in your calculator when you enter this stuff. So, let's scroll down. Excuse me. To to letter A. And let's put in our information. What's X? What's the count? 109. What's N? It's 1,520. Whoa, guys, I screwed up completely. Don't do, that was horrible. Guys, we need to do a one prop Z test. We're conducting a test of hypothesis, not a confidence interval. Darn it. First mistake I ever made. It's not. Now, this looks a lot better. What are we testing here? Well, we're testing 5.8%. Don't ever use the percentage. We have 109 out of 520 or 1,520. And what does our alternative sign look like? It points to the right. So choose the one that points to the right. Hit calculate. We got tunnel vision on one number. Now notice this is no longer a t, it's a z because it's a different test for a different type of problem. This is a percentage problem. They work by a z distribution. Again, those are the kinds of things that I tell you. But our p-value is 0.0111. Right here, this p-value. 0.0111. Not to be confused with this p-value. This p-value is the percentage of the population that fails its drug test. This is not a p, it's a p-value. I wish they wrote p-value out there to distinguish the difference between that and that. This is a p-value. So a p-value here is 0.011. Our alpha and the problem was 0.05. Clearly, 0.011 is less than 0.05. So guys, because of this, we would reject the null. So when you reject the null, you think of drawing a line through the null. There is significant evidence to support that the percentage of applicants who fail their initial drug screening is higher in Southern Ohio than the national claim of 5.8%. We reject the null. We reject the claim that is 5.8% or lower. And we conclude the alternative here that is higher than 5.8%. Now, I don't know about you, but if I were somebody that cared about this stuff, I would want to know, well, you tell me it's higher than 5.8. Well, what is it? Well, some people, well, it's 7.2. No, it's not 7.2. It's 7.2 for these 1,520 people. We are trying to make a more general statement here. And we make a more general statement using an estimate using a confidence interval. So that's what I would do here. I would go, I was dying to do it earlier because I knew it was coming. I'd go use a confidence interval. And I'd use this sample of 109 out of 1,520 with a 0.95 probability because I have a 0.05 level of. And I would conclude, therefore, that the percentage of job applicants is somewhere between 5.87% to 8.47%, using the information from that.